This is Tariq Nazir from UNSW Sydney. I did my PhD from here, from UNSW in electrical engineering. And currently I'm working in a School of Mechanical and Manufacturing Engineering. And mainly I'm working in a fire research now. And my PhD work was more related to fires, but more is related to electrical fires. So today the title of my presentation is the role of thermal conductivity on electrical tracking failure of the high voltage outdoor insulators. Yeah, today I'm going to talk. I will give you a little bit background of the work, like what is the background of that, and what are my working aims for that project, and what type of insulating materials we use, and how I prepare the insulating materials, and what experimental setup I use, and outcomes, and later at the end we will discuss about the conclusions of the work. The background here we can see high voltage outdoor insulators used on primary transmission as well, on a secondary distribution level as well. The role of the insulators is to provide support to the live high voltage conductors. So from the one end, they are connected with the live conductors, and the one end is, we usually call it the dead end, is connected with the poles. The old technology of the insulators is ceramic and the glass-based insulators. But since the last 3 decades, there is a major development in a polymeric insulator. So usually the pure polymers couldn't be used for the manufacturing of the insulators because they don't have a good mechanical strength. And another parameter is like we need some polymer that should be highly hydrophobic and have a very good weathering resistance. So usually we add some additives, is usually micro or nano additives, inorganic fillers we usually add with the pure polymers to get the required properties of the polymers to be used as an insulator. So that's why we call them the composite insulators. So there are several issues with the polymeric insulators when it work in outdoor atmosphere. One is a major problem is the corona. Like corona is like is a plasma, is composed of electronic species and the UV light, so that can deteriorate the polymeric material. And another problem is like with the passage of service, when pollution is accumulated on the surface of the polymeric insulators. So in the presence of some moisture or even sometimes light rain as well, that can initiate the electrical dry band arcing due to high leakage current on the surface of the insulators, and that high leakage current can easily increase the surface temperature on the insulators, and that temperature can thermally depolymerize the polymeric surface. So, and even sometimes we can see some flammability as well on the surface of the insulator. So that the carbon path, that one is that one is actually called the electrical tracking, and that one is called erosion on the insulator. So both, for reliable power delivery, we must need like the insulating materials must have a very good high erosion and the tracking resistance. So for reliable power delivery. So that work is related to more like how we can impede that problem. So the aims, how to impede the tracking and the erosion failure of the outdoor insulators, and how thermal properties impact on the tracking and erosion properties, because it's directly correlated with the leakage current amount and how much heat is accumulated on the surface of the insulator. So silicon rubber is usually used for the outdoor insulation. The reason being because the polymer is highly hydrophobic and flexible. So in the pure form, we cannot use this pure silicon rubber, cannot be used as an outdoor insulator because the mechanical strength is not good enough. So we usually have to use some inorganic additives in that. So for my experiment, I use two part, is a room temperature vulcanized liquid silicon rubber, RDV615, part A and part B. Part A is the main polymer, main matrix, and part B used as a hardener. And the fillers in this work, I have used 3 different fillers. Inorganic additives, we cannot use the salt additives in this type of work because that insulation have to be used on a high voltage. So we we want a very good insulation, good tracking resistance. In the meantime, that insulation should have very good electrical insulation properties as well. So we have to, the bandwidth is very narrow when we are choosing the fillers for high voltage application. So I have used the ATH. Currently, the industries are using ATH, aluminum trihydrate. And the second one, I compare the performance of ATH with the aluminum nitride and the bronze nitride. So here is the SCM micrographs. That one is showing the ALN and the bronze nitride. That one, the particle size is around 5 micrometer. The sample preparation is pretty simple. It's a very straightforward. We have to use a mechanical mixer. We have to use the part A of the liquid silicon rubber. We have to add our additives in that, in the polymer, but we have to be careful, like degassing should be, we have to take degassing step should be taken very carefully, because we shouldn't want any moisture or air trapped in the insulation sample, because if the air is trapped in the insulation, that can start electrical discharges in that. So we use the mechanical mixer, and after that we have to use the sonication. That is the water bath sonication. Usually the guys, like the researchers who are working in this area, they know the sonicator. So then at the end of that, we have to degas all the matrix, and then we have to put the part B. The part B 10:1, 10 is the part A of the polymer, and B is the hardener. We have to add part B is a 10:1. So that depends on the supplier. So they tuned that ratio. Even we can use 1:1 as well, but it depends on what batch of PDMS you guys are using. So curing was done on a high temperature, 150. After the mixing, the samples were, all the matrix were poured into the molds, and the molds were placed in a vacuum oven around 150-degree temperature for half an hour for the curing. And the samples were cured around 50 millimeter into 120 millimeter and the 6 millimeter thickness. And these samples were chosen according to IEC standard 60587. So this standard defined the protocol, how we have to perform the tracking in a ROIN experiment. So this one is the experimental setup according to 60587. So in the 60587, we have to mount the samples on an insulating support. That is the insulating sample here. So, and second one, we have to apply the high voltage on with that. So high voltage have to apply with the test transformer. And how much we will apply high voltage, what will be the flow rate of the contamination solution, that one is defined in the standard. So we have to follow all the instructions according to standard. So here is ammonium chloride solution. So ammonium chloride solution we have to fed here on the top HV electrode. HV is connected on the top electrode. The bottom one is connected with the ground. Here is the infrared thermal imager to capture the thermography, to capture the temperature on the surface of the insulation. And we have to, meantime, we have to measure the leakage current as well. So this one is a laboratory setup. So we have to capture the thermal images. Meantime, at the end of the experiment, we will measure the physical tracking in a ROIN. We have to measure the leakage current, and separately we have to measure the thermal conductivity of the insulation as well. So here's the outcomes. The first, at the end of the experiment, is a 4-hour experiment, and is a total 4-hour experiment. And the 4-hour experiment, in the initial hour, we have to start experiment with the 3 kV. We have to apply 3 kV, and this contamination solution flow rate is 0.3 milliliter per minute. And then every hour we have to ramp up the voltage by 250 volt per hour. So total experiment lasts for 4 hours. So at the end of the experiment, that is the position. That is the situation of the samples with 3 different additives. Here's the top electrode, here's the bottom electrode. So this one is the carbon tracking, that path is showing the carbonized tracking. Actually, we shouldn't want any tracking because it acts as a conductor. So that's why it's reduced the insulation properties sharply. So we shouldn't want any tracking on the insulation. So with the three different fillers, ATH, ALN, and the BN, we compare the performance of three different fillers. And if we, here we look at the eroded masses. So this one is the pure silicon. So eroded mass is quite high. So if we compare between ATH, ALN, and the BN, we have find the lower, we have measured the lower amount of eroded mass in the BN sample, and even in the BN sample is linearly decreasing with the amount of details. So higher in a 5 WT%. The same pattern is observed in the tracking length. We have to physically measure the tracking length, like what is the tracking length. So that one, even with the BN, we have seen very good results, and followed by the ATH and the ALN doesn't perform well, same like unfilled silicon rubber. So here's the leakage current. The leakage current is directly correlated with the tracking in erosion, because leakage current make different hotspots on the insulation, and once the temperature is increased on the hotspot during the dry band arcing, so that dry band arcing easily can deteriorate the insulation and can start electrical tracking. So we have to continuously measure the leakage current on the surface of the insulator. So we have measured the instantaneous current over the 5-minute period, around 300 seconds, and then we have calculated the RMS current. So here we have a look. At the start of the experiment, the leakage current is quite low in the all 4 samples, pure, ALN, ATH, and with the BN as well. So it's linearly increasing. We can see in the last hour of the experiment, the increment in the leakage current is quite high. So the high current is seen in the pure silicon rubber insulation and in the ALN sample. And here we can see the green line is showing the leakage current in the BN sample. And in the BN, the leakage current is relatively much lower if we compare with its counterparts. Here we look at the leakage current over the complete duration of the tracking experiment. Here the leakage current is linearly increasing, and at the end of the experiment we have seen much lower leakage current in the BN with the BN additives, but much higher current in the ALN and the pure silicon rubber. So still ATH and the BN, the performance of ATH and BN is found comparable and quite good. Here is the infrared thermography. We have to measure the temperature distribution on the surface of the insulation. Here we can see the main heat is accumulated in the middle of each sample, because the liquid is flowing in the middle of the sample. So major dry band arcing is seen in the middle of the sample. So main heat is accumulated in the middle of the sample. Similarly, like the leakage current, the temperature on the surface of the sample is increasing linearly. At the first hour, the maximum temperature is seen around 150 degree in ATH and the ALN. But the main temperature increment, because the temperature is directly correlated with the leakage current, so that's why we've seen both the leakage current and the thermal accumulation higher in the last hour of the experiment. So if we look at the last hour of the experiment, at 3.5 hours of the test, the highest temperature is seen in the ALN and the pure silicon insulation. So that one is around over 450 degree. But if on the other side, comparatively in the ATH and the BN, the thermal accumulation, the temperature, peak temperature is seen significantly lower, is around 120 or 150 degree of the C. So why this is happening? Why the ATH and especially the BN, boron nitride, is performing too good? The reason is we measure experimentally, we measure the thermal conductivity of each sample. And thermal conductivity is linearly increased with the addition, but with the BN, because BN is an inert, inorganic filler, and that can increase the thermal conductivity of the insulation, and at the same time it can retain good electrical insulation properties as well. So with from 5 to 30, at the 30 weight percentage of the BN and ATH and ALN, we can see the substantial increment in the PN filled samples with 30%. Pure silicon have a very low thermal conductivity at 0.109. But when the particle contents reach around 30%, we can see the thermal conductivity enhanced to 0.287 in case of ATH and 0.249 in case of ALN, but with the PN it's substantially increased to 0.745. So that could be the one reason, because the thermal conductivity is higher in the insulation. So during the tracking and erosion, during the heat accumulation, because the thermal conductivity is higher, so that thermal conductivity can conduct heat very easily in the ambient and can reduce temperature in the middle of the sample. So that makes a lot of sense. So the conclusion is the experimental results revealed that the resistance against tracking and erosion of the PN composite was significantly improved comparative to ATH and ALN. Physical tracking, erosion, and the leakage current and the surface temperature all are measured significantly lower in the PN brown nitride filled silicon rubber samples. The gain in the thermal conductivity is measured about, in the PN is measured about 6.8 times. 6.8 times higher thermal conductivity is observed relative to 2.6 and 2.3 times in ATH and ALN. So that increment is very huge. It's a very good increment. So that's why we clearly seen a huge impact in the experimental result. So results suggest that the significant increment in the thermal conduction conducts heat out, like I already explained, like higher the thermal conductivity, so that can conduct heat quickly in the ambient, and that can reduce temperature in the discharge region. So that is the major reason how thermal conductivity can improve, perform better in terms of tracking and erosion. So that's the end of my presentation, and here is my profile links on the UNSW research, LinkedIn, Twitter. Anyway, if you guys have any question, you can ask me, and you can follow me on using those links given in the slide. Thank you.
Thank you, Professor. Thank you for your wonderful presentation. Thank you, Professor Nazir. I hope everybody enjoyed his presentation. I'll leave some time here for any comments or questions. You can please ask Professor Nazir.
10:45. Okay, till we have 5 minutes.
May I ask something?
Yeah, sure, sir.
Okay, thank you, Professor Nazir, for your excellent presentation and experimental based. So yeah, I did experimental, but now it is mainly theoretical because I don't have experimental facilities. I'm also experimentalist and theorist. Anyway, so you did good work. So I have a quick question. You said you are using IEC 680 series. If
60587, yeah.
605, that is 60 series, that's fine.
Yeah.
Can you use 6 on series? Because I used to 6 on 850 series. Are there any possibility to change that on how the impact on the result and the research outcome? Is it possible or not? I ask this question other places also.
Yeah, because for the tracking and erosion, we have a different standard. It depends on what is our targeted application.
Yeah.
So if we are using the outdoor insulation, that one have a more pollution problem on the outdoor insulators. So we must need some conductive water have to flow on the surface of the insulator. So IEC designed that protocol. That one is 60587, but I forget the name of the ASTM standard. Usually Canadian and American universities use that ASTM standard. Okay, but on the other side, when we come to other insulation like the cable one or the motor insulation, so that one is a different tracking and erosion standard. That doesn't belong to contamination solution. So that they perform that one without that contaminant solution, because in the motor, that is pollution is not a problem there. So there is some other scenario. So it depends on the application. What is the targeted application? So we have to choose a standard according to that.
So in your group, Tuan is there, right?
Yeah,
in
Tuan was my
electrical engineering.
PhD. Yeah, Tuan was my PhD supervisor, and I finished PhD in 2018.
Yeah,
And
I know
now
him.
I'm
That's why I'm
working in a
asking.
yeah. Now I did my PhD with him. So now I moved to mechanical engineering. I'm working on an industrial project. So this one is more fire research, ARC Fire Training Center for Fire and Safety. So we are working on that. So this one is more commercialization and this kind of research now.
Anyway, thank you, Professor Nazir. Good explanation. I asked about Tuan. Anyway, so we can communicate later on. I can give the chance to others.
I will contact you.
Yeah, no problem at all. So I think someone can ask some question, not only me. Thank you.
Yeah.
Thanks again for the presentation.
Yeah, thank you, sir. Cheers.